So in our last class, we had discussed the importance of placement of the amplifier, right? So if the amplifier is placed after the loss, even the losses are uh, amplified, okay? And we saw that in the form of numbers as well, where we got 185, then here we got 1136, right? Okay. So today we will move on to our next topic, which is nothing but your carrier to noise ratio. Okay. And this is in short also termed as CNR. So carrier to noise ratio, how much of noise to be enabled, okay, for the information not to be lost. Okay, so how much of noise can it accept maximum? So that is what is meant by our carrier to noise ratio. Okay, so it's a measure of performance of a satellite link, uh, and it's the ratio of carrier power to the noise power. So C carrier power, N noise power, okay, which is also equal to received power, PR and your noise power. Okay. So the receiver input and link budget calculations are often concerned with determining this ratio. Conventionally, the ratio is denoted by C by N or CNR, which is equivalent to PR by PN, okay, in terms of decibels, right? So here you can see that your losses are, considered your EIRP, okay. Here I have taken it as plus because it is gain, okay, because ultimately we are finding out the noises, right? So minus losses, minus K, okay, TS and your DR, right? So your G by T ratio is a key parameter in specifying the receiving system performance. So based on this number, we find out as to what is your system performance, how much of noise that it can take, how much of flexibility that your system has. So the antenna gain GR and the system noise temperature ES, okay, TS we have seen, which is your system noise, can be combined. Okay, so your antenna gain, okay, GR and your TS. So this is taken as dB Kelvin inverse because this was a ratio. Therefore, the final equation, okay, the final equation becomes EIRP plus G by T losses minus K minus Vn. You will have to know all of this, okay, just for substituting the values, okay. So again, here we can split up things. Your carrier to noise ratio can be taken as C by N naught into Bn, right, which is nothing but your noise of the bandwidth. The ratio of carrier power to noise power density may be the quantity actually required. Since Pn is equal to KTN Bn, then we have this formula. Okay. So ultimately, what we are trying to do here is C by N naught is equal to C by N plus noise, which is existing in the full Bn. Okay. So C by N is a true value, okay, which means it's a true power ratio in units of decibels. So this C by N, most of the times, as I've told you, those in square brackets are in terms of decibels. It is related to about 1 hertz or dB hertz. Okay. Thus, the units of C by N naught are dB hertz. When we substitute this equation, okay, for C by N, so ultimately we are going to get this final equation, EIRP G by T losses minus K. So we will see how we are going to use that in our problem. So we have an example here where a link budget calculation at 12 gigahertz, okay, so which means we know the operating frequency, okay, at which it's functioning, Then free space loss is about 206, okay, loss. Then pointing the antenna loss is 1 dB. Okay, all these values we'll have to note down, and accordingly we can add them up. Then atmospheric loss is 2 dB. The receiver is having 19.5 dB per Kelvin, and receiver feeder loss is 1 dB. Like C by N, spectral density ratio. So ultimately, we have to know which formula to be employed and what values are to be substituted. So if we have these two details, then it becomes easy for us to find out. So the values are to be noted down, okay, and we will try and incorporate those values into it. So we'll have to know the Boltzmann constant, okay, in terms of decilogs, okay, small conversion needs to be done. Few values are constants, okay, wherein you can remember those. The data are best presented in the tabulation form and in fact lend themselves readily to spreadsheet type computations. Okay, so what we have done is we have just taken all the values and put in the form of tabulation. So that makes our job still simpler. And losses are entered as negative numbers, okay, to take account the minus sign. Then Boltzmann constant, if we equate it to the decilog form, then it becomes a 228.6. Okay, so now we will see this tabulation, and you can understand as to what all losses were mentioned. So free space loss, atmospheric loss, antenna pointing loss, feeder loss. Polarization was not mentioned, so we have put as 0. Then receiver G by T ratio, then the EIRP, okay, then your Boltzmann constant, then your Boltzmann constant value, okay. So all these are taken into consideration. Okay. So now I'll have to use my C by N, which is equation on 12.38, okay, which I have used. Okay, so this equation is what I'm going to employ. Okay, just make a note of that equation. Okay, so this will be employed, and the final result will be 86.10. You can just compute them, okay, with the help of this total losses. You can put it here, then G by T, EIRP, and K, and finally you should be getting about 86. Okay, fine. So now we will have to talk about the uplink. Okay. Now all the notations are just the same, but you can just find that there is a U here, okay, U for everything. Which is representing specifically the uplink, signals that are transmitted from the base station to uh, the satellite. The uplink of a satellite circuit is one in which the Earth station is transmitting the signal and the satellite is in the receiving end. Fine. So the same equation we have used here, but then as I mentioned, we are employing U, okay, U, referring to the uplink. Yeah. that the signal is being transmitted. Then this equation, the values to be used are earth station EIRP. Okay, so we have specific values for the earth station. So those values alone we'll be using. We will not be using those values which are specifically meant for the satellite. Okay. The free space loss and other losses which are frequently dependent are calculated for the uplink, and the resulting C by N ratio, okay, is that which appears at the satellite receiver. So whatever losses that is happening, uh, those losses are appearing at the receiver of your satellite, okay, because these signals have to pass through, it has to go through the atmospheric losses and many other such losses, right? In some situations, the flux density appearing at the satellite receiver antenna is specified rather than the earth station EIRP, right? So this is a very special case where there can be occurrence of flux density at the receiver side. So which means even though it doesn't happen here at the base station, okay, it can happen at the satellite point. Okay, so that flux density is also taken into consideration. So what is this flux density? It is because of the TWTA. Remember, we spoke about the electron gun and how the electrons are made in a straight path. They are made to move in a straight path. So this is actually available on your satellite. Okay. So this is also contributing to the error. So we add it up when the uplink is done. So the traveling wave tube amplifier in satellite transponder exhibits the power output saturation. So we had seen that in the figure. Okay, so I've just put it here for your reference so that you can get back to the specific figure. The flux density required at the receiving antenna to produce saturation of TWTA is termed as saturation flux. Okay, so the one which is appearing at your traveling wave tube amplifier. The saturation flux density is specified quantity, okay, where in link budget calculations and knowing it, one can calculate the required EIRP at the earth station. Okay. So once we have these values, we can actually easily calculate. So we'll have to consider the equation which was in 12.6 and we will employ the same here. So there are few notations, okay, which you have to take care of. Okay, your psi m is equal to EIRP by 4 pi r square. Normally we have seen this in our communications, right? 4 pi r square, the free space loss, right? So it is nothing but your EIRP plus 10 log 1 by 4 pi r square. So I'm just taking it this side. Then FSL is your free space loss, okay? 10 log lambda square by 4 pi. So ultimately, okay, the final value that you'll have to remember, okay, is your EIRP minus free space loss and minus your 10 log lambda square by 4 pi. Okay, so this lambda square by 4 pi, this term has the dimensions and area. Okay, so it is dependent on how your antennas are and it's dependent on those parameters. Okay, and it is specifically referring to something called isotropic antenna. Okay, so A naught. So what we will do is we will refer to this whole term, okay, to this whole term as A naught. Okay, so A naught is equal to 10 log lambda square by 4 pi. So our equation, okay, our equation changes where there are few preset values. As I told you, there are few preset values. Since the frequency rather wavelength is normally known, the frequency f in gigahertz can be rewritten. Okay, so this value here, okay, 1 by 4 pi, and 10 log can be actually written as 21.45 plus 20 log f. Okay, so we will be using this in fact much more than this equation here. Okay, then your EIRP is a combination of psi m, okay, which is your flux, A naught and FSL. FSL is what? Free space loss. So Ultimately, if we still have to find out or dig into the number of losses um, contributing, okay, then we can even add the AA, which is atmospheric loss, okay, and your polarization loss, and then your AML, okay, fine. So we can actually keep adding these losses. So I have summarized, okay, all the types of losses in the table, where you can actually just look into. Just give me a moment. I have summarized the losses and I have mentioned their meanings as well. Okay, so we will come across it in a while. Fine. So in terms of total losses, the EIRP, okay, is nothing but your psi m E naught, then your losses, and then your RF. Okay. Now for clear sky conditions, the minimum value of EIRP, where your Earth station, okay, should provide a given flux density. Okay, so we need to have certain values to be maintained. If those values are not maintained, then the losses are high. Okay, fine. So let us see one example, and we'll try and understand as to what these are. The uplink operates at f is equal to 14 gigahertz, and flux density required to saturate the transponder is about 120. Okay, free space is about 207 decibels. Okay, the loss, and the other propagation losses is about 2 dB. Now, when they say other, you have to just take this as a loss. You cannot specifically say to which loss this 2 dB is for. Okay, then the clear sky. Okay, clear sky conditions they are assuming, and they are telling us to uh, take the RFL as negligible, which means do not consider it at all. So at 14 gigahertz, okay, first calculate A naught, okay, A naught, so F value 20 log F, right? So 20 log 14 comes here. So you will get your A naught value. So the losses, you will be having this formula, okay? So um, your total losses, okay, plus 207, okay, plus 2, which is about 209. And how are we getting these losses? Okay, 2 is here, right? Then 207 is here, okay, the free space loss. So we are adding those two, and we are getting about 209 dB. So we'll have to add those as well, okay, losses, and then your A naught, which is minus 44.37. And to this we have to add 209, because this is our free space loss. Okay, and finally that we will be getting is about 44.63 dB watts. Okay, so ultimately you should know which formula to refer to. Okay, so we have referred to this formula here. Yeah, we have referred to this formula here, and F is substituted, A naught is taken. Once we have this A naught, okay, then we try and put those values here in our formula. Okay, right. So now there's a concept called input backoff, okay, where we try to change the values of input and make sure that it gives us the maximum output value. Okay, so that is called your input backoff. So in order to have that, okay, so we will just look into few of the concepts here. Number of carriers are present simultaneously in TWTA, which is nothing but your traveling wave tube amplifier. The operating point must be backed off to a linear portion. I think I could have mentioned the graph. Okay, so we are referring to the graph which was previously there. Okay. To reduce the effects of intermodulation distortion. So what we have to do, we have to reduce the values of input, try and make sure that these values come a little bit in the proper value, which means we need proper output values. Okay. Since multiple carrier operation occurs with frequency division, okay, multiple operations happen. The point to be made here is back off must be allowed for link budget calculations. So there are a lot of considerations, that is to be done with regards to your communication. It is not just because of free space loss, or it is not just because of the atmospheric effects, okay, and it's not only because of this polarization. Many things are there, okay, polarization losses, many things are there. So we will have to consider, you know that for your uh, calculations for losses. Okay, right. The point is the back off, okay, that we are talking about. And suppose the saturation flux for single carrier operation is known, then we can actually take few more considerations. Okay, so which means your input back off will be specified for multiple carrier operation, which is referred to the single carrier saturation level. So what we are trying to do here is, if the values are going too high in the graph, okay, we try to bring them a little down so that it becomes proper. Okay. Sometimes too high values also can cause a lot of distortions, a lot of noise, a lot of degradation. Okay, so we try to pull back the output by reducing the input. It is just like, giving it less food and making sure that the output is less. It comes um, in the proper range. Okay. The Earth station EIRP will have to be reduced by specified back off, resulting in an uplink value. So which means your EIRP should be in consideration with the back off. So, so BO and I refers to back off at the input side. Although some control of the input and transponder power amplifier is possible through the ground and your telemetry tracking and control station. Okay. So even that is possible. If you have to reduce your signal, uh, then you have the option to control it from the base station also. Okay, not only just reducing the input, but in the base station also you can reduce it and make sure that your output values are coming in proper desired range. The input back off is normally achieved through reduction in VAR. So consider this equation, okay, where you have your surface level flux, okay, your back off, your G by T, your RFLs, okay, many such factors. Okay, so let's take an example, and we will add a back off of about 11 dB, okay, to a flux density of about 91.4, and then we will calculate, okay, with consideration of feeder loss of 0.6, and C by N we will calculate. Okay, so here we see that in the previous example, okay, we have found out that A naught is minus 44.37. It is actually connecting to a previous example. Okay, the same thing, just that, we have added few more values here, back off and other values, right? So just go through this. So here we can also see that your K is equal to minus 228.6. Okay, so your input back off is entered as negative numbers because it is a kind of loss that we are giving to. So we summarize things and we try to put it here in the form of a tabulation. Okay, and we calculate it to be about 74.5. Okay, since paid margins have not been included, it applies for clear sky conditions. So which means we have not taken this fading into consideration. Okay, wherein the signals have the option, or where signals are prone to fading because of the atmospheric conditions. So we have considered here there is zero fading, which means the sky is clear and the signal is just passing through without any loss. Okay. So this fading occurs normally when there is a rainfall. Okay, so even when it is not rainy, when it's too cloudy, and when it's misty and foggy, there can be a lot of loss. Okay. Next concept that we'll be seeing is about the Earth station. Okay, so the Earth station has to supply the radiated power plus transmit feeder losses. Okay, and this is denoted by TFL. Okay, so when I use in square bracket, then it's a decibel. So this is nothing but your transmitter feeder loss, TFL. This include the waveguide, filter, coupler losses. Okay, so there are a lot of things to be considered actually. Okay, so your Earth station, okay, so it is referred to as HPA, is equal to AARP plus GT, okay, the total gain plus your feeder losses, okay, your transmitter feeder losses. Okay, the EIRP is given by the equation which we saw previously, and that also is a part of back off. Okay, so back off also to be considered here. So the Earth station's back off is taken as HPA, okay, and it will be operated at the back off power level so that it provides the required output. So I think you have now understood the concept of back off, right? It's very simple, wherein we reduce the input to make sure that outputs are in a proper range. Okay, so sometimes due to higher inputs, okay, the outputs are amplified at a much higher level and losses are high. So in order to reduce that, in simple, we just reduce the input values. So whatever we discussed so far will be the same or applicable, um, the ones we discussed in uplink to the downlink as well. The notations change here with D, the subscript D. Okay. So this means that we are receiving signals from the satellite, and the final destination is going to be the Earth station. The downlink of satellite circuit is the one in which the satellite is transmitting the signal and the Earth station is receiving it. Okay. One more thing that you all can keep in mind is uplink takes a lot of frequency, which means it takes a lot of power, but downlink doesn't take much. So which means I do not need much power to transmit my signal from the satellite to the base station. Okay, fine. So these values are used, and the receiver feeder losses and the other G by T ratios are also considered. The free space and other losses are calculated from the down frequency, and we calculate the carrier to noise ratio, how much of noise is allowed, how much of carrier, what is the maximum allowable noise in order for my signal to transmit. So this is going to be my equation considering G by T ratio, okay, and EIRP losses, as usual, K Boltzmann constant, and the bandwidth, okay, this bandwidth B. So we'll have another example here, okay, where we consider TV signal which occupies a full transponder bandwidth of 36. Remember, we had 36 and 4 is used for guard band, right? And it must operate at a carrier to noise ratio uh, at the destination earth station of 22 dB, and the total transmission losses are 200, and the destination earth station is about 31 decibels per Kelvin. To calculate the satellite EIRP required, so the total EIRP. So here they have asked only EIRP, and they're telling that it's a satellite TV signal, so which means I have to use the downlink formula. Okay, so we know that our K is 228.6. Okay, and the losses totally I can give it as 200. So again, we use the tabulation method here. Okay, we use C by N. GT is also given, which is about 31, right? See, 31 is here. Okay, then the total losses. Now in this losses, it might be your atmospheric loss, it can be your polarization loss. Okay, so many other such things. Okay, and this dB we can even convert it using that 10 raised to formula, right? So we have another problem here, okay, which talks about our QPSK signal, okay, and we will just look into it, and we'll try and understand as to how to go about solving this problem. Okay, so we'll be looking into this problem, okay, where a QPSK signal is transmitted by satellite, okay, and it has a raised cosine filtering, which is having a roll-off factor of 0.2, and your bit error rate BER is 10 raised to minus 5. The satellite downlink, the losses amounts to about 200 dB, so which means it's transmitting from the satellite. The receiving earth station has G by T ratio of 32 decibels per Kelvin inverse, and the transponder bandwidth is 36 megahertz. Calculate the bit rate which can be accommodated and what is the EIRP that is required. Okay, what is the power required, right? So we know that the formula, okay, RB, okay, RB, which is nothing but your roll-off factor, okay, roll-off factor. So you will have to remember this formula. RB is equal to 2B plus 1 by uh, 2B divided by 1 plus. So multiply this with your bandwidth, okay, which is 36, and your 1.2 is your roll-off factor, okay. Sorry, 0.2 is your roll-off factor, 0.2 plus 1. So this gives us RB, which is about 60 Mbps, okay, and this one we converted to 10 log and the values, so dB bits per second, okay, because they are telling us to calculate the BER, right? Okay. For BR is 10 raised to minus 5, okay. So there's a figure actually, okay. I have given the figure number, which is about 10.17, okay, and we have to take the values from there, okay, and it gives us approximately about 9.6. Okay, so this is a standard value, just like your tabulations, okay, your tables. Then our C by N is equal to EB by N naught plus RP. So this one we have calculated it as 77.78 plus our RP, which is about 9.6. So these two values are added, okay, because I wanted them in terms of decibels, right? So I will add them up and I will get 87. So my total EIRP will be C by N minus GT. As I told you, it's a transmitting signal, so which means we are receiving. So it's a downlink uh, frequency that is considered, plus losses plus Boltzmann constant. So all these are considered, and we approximately get about 26.8 decibel. So the main thing here is conversion to the dB form, and this roll off factor that you will have to remember the formula. Just like how we had our input back off, the output back off also can be done, and that is denoted by BO, O referring to output. So the input back off is employed, a corresponding output back off must be allowed for satellite EIRP. Okay, so this is the curve that I was actually talking about, where the best operating point will be here, and after this point, okay, it gets into a saturation point. So we do not want that. So what I will do is I will reduce my input, and I will make sure that it is falling only in this line. Okay, so I am interested only at this point. So once I have that point, then it becomes easy for me to try and analyze. Okay, so I will try and bring them just below this point, so that I will not have this kind of saturations happening. Okay, I will not have this kind of saturations happening. So I will be concentrating on values only up till here. Okay, and then my input values are also concentrated in those levels, and I will make sure that my output doesn't cross this point, okay, wherein it actually gets into something called saturation point. I do not want my outputs to get saturated, but instead I want them to linearly or exponentially climb up the values. Okay, fine. So as a rule of thumb, frequently used is to take the output back off as the point on the curve, which is about 5 dB below the uh, polarized value. Since the linear portion gives a 1:1 change in decibels, now this is important here. Okay, output back off is equal to input back off minus 5 dB, how much ever is your input back off. Okay, so you minus 5 dB, that gives your output back off values. Okay. For example, if I have 11 dB, okay, then minus 5 is going to give 6 dB. So this 6 dB is going to be my output backoff. Similarly, I will have values for these, and considering when it's a downlink, okay, the output backoff is given as BO, and brackets represent the decibel form, okay, and O represents your output. And accordingly, you will have losses. Okay, so these losses can be your atmospheric loss, okay, and various other uh, rain-based or the rain attenuation, okay, all those. Fine. Okay, so this is the relation that we spoke about. So another example that we can actually look into is the specified parameters for a downlink satellite is about 25 decibels, and the output backoff is 6. Free space loss is 196. You always keep in mind, whenever there are multiple values given like this, try to note them one by one, and immediately map it to only those values, because there can be chances that instead of output backoff, okay, you might put the 6 dB in feeder space loss. Okay, so just make sure that you write down and transfer the values immediately onto your scripts. Okay, fine. The Earth station GT is about 41 dB. Okay, so the best thing to do is put them in the form of this kind of tabulation. What is the quantity, and is it in the form of decilogs or not, so that you can do the conversion later. Okay, right. So as with uplink calculations, the work is best set out in tabulation and with the minus signs, because all these losses are taken as minus. Free space loss, other losses, then output back off is 6. Okay, so minus 6, earth station, then your k minus k, so minus I take here, so minus I don't give it here at the number. For the uplink, the saturation flux density of the satellite receiver is a specified quantity. For downlink, there is no need to know the saturation flux density at the Earth's receiver, because this flux density that we are talking about will be with respect to TWTA, traveling wave tube amplifier, and this is present in the satellite, right? So while downlink, we do not have to consider that specific loss. Okay, and the signal is not used to saturate a power amplifier. Now, just now talking about your TWTA specifically, okay, the satellite power amplifier, which usually is TWTA, has to supply radiated power plus transmit feeder loss. So not only power, but even the losses are also transmitted along. Okay, as you saw those diagram, okay, where your cable losses are also transferred, and if we put the amplifier just before that or after that, how is the implication? So all this we have seen them across. These losses include waveguide, filter, coupler, okay, all these, right? So we can put it in the form of equations and put it as P TWTA is equal to EARP, downlink time, GT, and your TFL. This is nothing but your transmit filter loss. Okay. So the saturated power, okay, S is nothing but saturated power, is given by TWTA plus output back of how much I have reduced. So we can take a problem now and understand the application of the formula. Okay, a satellite is operated at an EIRP of 56 dB watts with an output back of 6 dB. The transmitter feeder loss, which is TFL, is 2 dB, and the antenna gain, okay, is 50 dB. Calculate the total TWTA. So, which means they are talking of the power of TWTA, downlink, GT is already given as 50, okay, the gain, and TFL is given as 2. Just substitute, you will get 8 dB, okay. Now, not only this, okay, you will have to add it with about 6, okay, because we have a back off here of 6, okay. So, totaling those values, we have 14 dB watts. See, the problems here are very simple. Question might seem to be very complex, okay, but if you know which formula to apply and how to extract data and which data in what form, is it in dB form, is it in decilog form, what form is it, if you try and understand, then it becomes very simple to solve problems. Okay, so I think we will stop here and we will continue with our next class, okay, which is your combined uplink and downlink. Whatever we studied so far was only separate with uplink and separate for downlink. So here we will be combining them both, and we will come out with few more equations and try and understand as to what exactly they are, and also with a problem. Okay. So any doubts up till now that we discussed so far? Okay, fine then.